Thank you all for coming. It's always a pleasure to be here with you all. Yeah, last summer I did an RU project in digital topology, although I'm not really going to talk about that project, although it's the same kind of basic area. Anyway, digital topology and a digital Borsuk-Ulam theorem. These are some things that I've been working on this summer. I actually decided, based on the RU project from last summer, I decided to write an article which I sent to Math Horizons, which is kind of an undergrad mathematics magazine. And it was, I've never written, they don't like it to be too technical, you know, and I've never really written in that style before. So some of that is in here, and then some other more technical stuff I wrote about a Borsuk-Ulam theorem. Anyway, let's get to it. So digital topology is about sets that look like this. This guy I designed for my Math Horizons paper. I shouldn't really say math. I mean, they haven't accepted it yet, so it's a paper that may or may not appear in Math Horizons. I originally used like a Space Invader graphic for this example, but the Space Invader is under copyright, and so I made my own thing, which is a little happier. My kids would see me working on this, and they liked this guy. I made like 10 different ones, and I like this one the best. They referred to him as Pappy because he's purple and happy. That's what they said. Yeah, that's cute. Anyway, so digital topology is about trying to do topology on things that look like that. And I want to consider this as a finite set of pixels in Z2. You know, I do not want to consider this as a subset of R2. That's what it looks like, but I want to think of it as just a bunch of finitely many points arranged in a certain way. And that's why I'd say in Z2, you imagine these pixels as sitting on the integer grid rather than on the real plane. You cannot, when you're doing this, you realize immediately, you actually can't use the subspace topology from R2 when you think of these guys on Z2. That's because actually, if you try that, you're not going to achieve, or you're not going to obtain anything that acts in the way you want topologically. It's a fact. I don't know how much point-set topology you guys know, but if you have a finite set, there are not many ways to put an actual topology on a finite set. And in particular, the only Hausdorff topology on a finite set is the discrete topology. So if you want to make a topology which resembles the topology from R2, it's not going to happen, basically. You're going to get the discrete topology, which is not really useful for anything. So you can use the subspace topology. I'm just trying to convince you that actually this requires a new kind of theory. It's not just, you can't just use topology from R2 or the geometry of R2 to try and handle sets like this. You have to come up with something different. So you can't use the subspace topology or any other natural topology. By that I mean Hausdorff. Yeah?
Clarification question. You said that the points are, I mean, the lattice points are the sort of the corners of the squares lattice points or the centers of the squares lattice points?
I think it's better to imagine it as the centers of the squares. But I want to think of this thing not as a bunch of pixels. I think of the pixels as sort of like atomic elements. Like the pixel itself doesn't have a corner or a center. It's a thing which is indivisible. So I'm never going to talk about the edge of a pixel or the middle of a pixel. It's just a pixel. By the way, please feel free to interrupt with any questions. So we need a special theory for this kind of a thing. Actually, a little diversion here. It's an interesting time now for digital topology. The theory, I would describe it as being still in its infancy, the mathematical theory, even though it was started in the 70s, which is not exactly infancy time frame. But today, surprisingly few mathematicians are working in this area. And it's not my sort of original training is not in digital topology. It's something I've gotten interested in the past couple of years. But anyway, you know, lots of people do very fancy digital image analysis. This is a really big deal. And these people get paid more than I do, probably. The thing is, these people, image analysis in industry is about getting stuff done, not about building theories. All right, and so the character of the work, I would say, is very different, and it's not really like mathematics, where we are trying to build theories which express certain ideas. If you work for Facebook and you're trying to identify people's faces without their consent in their pictures, you are not really concerned with building mathematical theories. It's just trying to get the job done so that Facebook can do whatever it's trying to do. And so I would say digital image analysis is something that many, many people are interested in. But mathematical digital topology, for whatever reason, is kind of a niche area these days. And I would say the practice of digital image analysis is way beyond the mathematical field of digital topology. The things that digital topologists are talking about are, to a layman's perspective, way less advanced than the kinds of things which are actually being done in the sort of real-world digital analysis. It's a strange kind of a thing. Here's a great example of that. This is the Paint Bucket tool. I got this from GIMP, which is like an open source version of Photoshop. If you ever use Photoshop or something like that, you're probably familiar with the Paint Bucket. It's a button which you click it somewhere and it just fills the inside of a region with a color or a pattern or whatever. I did some research on this and I couldn't find anything earlier than 1984. This was Mac Paint was one of like the launch pack-in software with the original Macintosh computer, and they had a graphics program called Mac Paint, which had this Paint Bucket tool in it. If you think about it, the reason this works, the reason it's possible to do this is because of the Jordan curve property in R2. That is, the idea is you click the paint bucket somewhere and it fills in a region. It fills in the inside of wherever you clicked. If that's going to work, there has to be such a thing as the inside of what you clicked on, all right? And it's a thing that hopefully you guys have heard of, the Jordan curve theorem. It says if you have a simple closed curve in the plane, then it has an inside and it has an outside, all right? This is one of those things that, if you tell this to a kid, they will think that's obvious, and everyone thinks that's obvious, although it's actually not really obvious, and it turns out to be really hard to prove. But this is the Jordan curve property in R2. But the Jordan curve theorem actually turns out to be messed up if you try to do it in Z2. For example, here's a thing which seems to have sort of two different insides. It divides the plane into three regions, right? One outside and two inside bits. But that thing, I hope you can see my ghetto fabulous path there. That path that I drew is a simple closed curve under the traditional definitions. That is, it's a loop which doesn't intersect itself, right? So I guess something is weird about the Jordan curve theorem in the digital plane in Z2, right? Maybe it's not. I mean, maybe the answer is like that just shouldn't count as a simple closed curve. And it turns out, so there are people who worked on digital Jordan curves theorems, and the work involves figuring out exactly what does it take for a curve to separate the plane into an inside or an outside. But there's a theory that's required for that, all right? It turns out this digital Jordan curve theorem was eventually proved using some fancy topological theory by Kalimsky and some other people. And this was actually one of the original big examples which got people interested in a real special digital topological theory. The Jordan curve theorem was one thing that people said, like, we need a new kind of topology for the digital plane that's not just the same as ordinary R2 topology. But work on this Jordan curve theorem continued into the 90s, right? Remember that paint bucket appeared in the 80s and maybe even earlier. So this is just a very specific example where the real-world applications, that is the paint bucket, which relies on the Jordan curve property, preceded the theoretical development. I mentioned this to Mark Demers, and he had his humorous retort was, it must have been like in the 80s, that thing was just grayed out. And then once they actually proved the Jordan curve theorem, then you could really use it, really click on it. Didn't actually work that way. Interesting fact. Actually, I think, I'm not a historian, I'm going to wax a little historical here, but I think this was actually the norm in mathematics before modern times. This is certainly the case in calculus. What I'm referring to is people were doing things in the real world before there was actually a real theoretical foundation for it in mathematics. This is a great quote from a math historian, Judith Grabiner. She said, first the derivative was used, then discovered, explored, and developed, and only then defined. You've probably heard a bit about the history, like specifically the notion of a limit. People have been thinking about limits forever since ancient times, but it wasn't until fairly recently that people were really describing limits in the way that you would recognize. So rigorously defined, I mean in terms of the epsilon delta definition. This apparently was done by Bolzano, but nobody really cared about it, or nobody thought it was very important in the 1810s. And then Cauchy, shortly after, actually, it seems that Cauchy didn't actually give the definition of epsilon and delta. When he defined what a limit was, he used some kind of what we would now describe as sort of hand-wavy nonsense to describe what a limit was. But inside of some of his proofs, he actually used something like epsilon delta arguments. So he didn't state it up front as a definition, but he seemed to be operating with that. But it wasn't until Weierstrass really sort of sealed the deal on the epsilon delta and showed that you could actually take all sorts of different things and encode them in this rigorous way. Anyway, I think that's the end of my historical diversion. All this to say, digital topology is still in that phase where people sort of in the quote-unquote real world are doing things that are a lot more advanced than mathematicians are comfortable with. And it's, I don't know how long that's going to continue. I imagine, 100 years from now, it'll be sort of equalized, but I don't actually know. Anyway, what I'm going to talk about is I'm going to refer to as Rosenfeld-style digital topology. So this is based on ideas that were kind of pioneered, as far as I can tell, in this paper called Digital Topology in 1979. This is actually, it was published in the Math Magazine, which is a MAA publication. It's very, very readable. You could go get this paper, read the whole thing, and you would understand every bit of it. It's a nice thing to check out if you're interested. Anyway, the basic idea here is we only care about the pixels and their adjacencies. When you do topology, as opposed to geometry, you could say one idea, or the basic concept of topology is it's something like geometry, but you're going to ignore angles and distances and things like that. You've got to say, what is it that we actually care about, and what is it that we don't so much care about? And in this style of digital topology, we care only about the pixels. What are the pixels and which ones are next to each other? That's it. All right? We don't care exactly where the pixels sit in the plane or what directions the adjacency. I mean, like an adjacency going up should be the same as one going to the side, something like that. All right? This is kind of like in geometry, or in topology, you ignore angles of things, but you do care when things are connected or not connected. So anyway, these three digital objects would be considered to be equivalent. That first one, I just sort of put one of the arms up when it used to go down, but those are actually, in this theory, they are homeomorphic topologically. And then the last one is just a rotation, which doesn't change the topology. All right? Whereas this is different. If you chop the guy in half, the reason that one on the bottom is different is because I broke a lot of the adjacencies, and the adjacencies is what's important in this digital topology model. All right? So all we care about are the points and their connections. Does this remind you of anything? Anyone want to fill in the blank here? Really, we're thinking of this object as a graph. Yeah, a combinatorial graph is a thing where all you care about are the points and the connections between the points. All right, we're thinking of this as a graph. So actually, this there are various different approaches to digital topology, and what this sort of Rosenfeld approach is often described as a graph theoretic approach, for exactly this reason. So we imagine each pixel is a vertex in the graph, and each adjacency between two pixels defines an edge in the graph. All right. Actually, there are, I would say, at least two natural ways to make this guy Pappy into a graph. Here they are. You could do this one on the left, or maybe that one on the right. I think those both seem to be natural ways to convert that into a graph. The difference would be on the right side, I am allowing diagonal adjacencies, and on the left side, I'm not. Right? One of my kids, when they saw this, she said, "Oh, that's like Pappy's skeleton." And then the other one said, "Yeah, that's what Pappy will look like when he's dead." Yeah. Anyway, so here's there's two different ways that you could decide what counts as being adjacent, and they're different, right? So here's the definition. I'm going to call these digital images. So a digital image is a pair, x, comma, kappa, where X is a set in Z2, that's like the set of the pixels, and kappa is a symmetric and anti-reflexive relation on X, which is called the adjacency relation, all right? So this sort of abstract digital image consists of what are the pixels, that's the X, and then kappa is a relation which describes which ones are adjacent to one another. This you should think is very similar to like a topological space is defined as a set together with a topology, or a metric space is a set together with a metric. This is a digital image is a set together with the adjacency relation. All right? I say symmetric, so it should be symmetric in order, like, if it weren't symmetric, then these graphs would be sort of directed graphs, which I don't want. And I also said anti-reflexive. That's just a convention. You don't call a pixel adjacent to itself. It's just not. It doesn't really matter. That's not so important. Anyway, choosing different adjacency relations gives you topologically different images. For example, in this case, the one on the right there is connected, but the one on the left is disconnected, right? So it really matters. It's not like, in metrics on Rn, you learn about, there's a whole bunch of different metrics, but they give you the same topology, so they're kind of equivalent to one another. Here, even the sort of ordinary or natural choice of adjacencies are not equivalent to one another topologically. All right, you could, if you want to give these names to these two schemes, you could call these, like the one on the left, maybe the rook adjacency, and the one on the right, the king adjacency. That's clever. Actually, nobody calls it that. I don't know if you think that's clever. I think those are good ideas, good names. I don't know. They're called C1 and C2. The one on the left is C1, and the one on the right is C2. Specifically so the C2 relation, this is the king one, you could define it in this way. So that little symbol there with the arrow, that means adjacent or equal according to C2. So X and Y are called adjacent according to C2 if their coordinates differ by at most 1 in either position. And if you think about it, that's what that first picture was. Both the coordinates can be different, but they can only differ by 1. All right. The rook adjacency would be this one. Their coordinates differ by at most 1 in one position and are equal in the other. That is, they have to match in one coordinate and they're different in the other coordinate by at most 1. All right? And this is why they're called C1 and C2, that the 1 and the 2 refer to how many positions are allowed to be different. C1 means one position can be different. C2 means both of them can be different. All right? For higher dimensional images, which we are going to talk about a bit later, you can define CK as X and Y are adjacent if and only if they differ in K positions and are equal otherwise. So that's that. For instance, in Z3, a digital image in Z3 is kind of like a Minecraft character, something which is three-dimensional but made up of blocks. So the C1 adjacency would be sort of only horizontal, vertical adjacencies, no diagonal. C2 adjacency allows face diagonals on cubes. That is, diagonals which have only 2 coordinates which are differing, whereas the C3 would additionally allow a solid diagonal which has all 3 coordinates changing at once. So this is in Z3. And in Z4, you can imagine there's a C1, C2, C3, and C4, which tell you what kinds of diagonals are allowed. What about color? All of this that I've been talking about have been technically, we would call these binary digital images, because all I'm talking about is what are the pixels. I'm not talking about pixels having colors. You could introduce color. A standard or an obvious way to do this would be you start with a digital image like I described, and then you also specify a function on X which just tells you the color at each pixel. So for an 8-bit grayscale, that would be each pixel doesn't really have a color, but it has a brightness. If it's 8-bit, then the brightness typically would be from 1 to 256 or 0 to 255. So it would be a function like this, which assigns each point gets a number from 0 to 255. And that little z there means this is like the integer interval, so that just all the numbers from 0 to 255, just the integers. All right, 8-bit color would be something like this. The codomain in this case would be 0 to 255 cubed. That is, usually color would be stored as like RGB vectors. So you'd have a certain red saturation, certain green, certain blue. And you need 3 dimensions to store the color in that case. Anyway, let's talk about the Borsuk-Ulam theorem. This is the other part of the title here. This is like one of my first mathematical loves. I can remember in my youth when I decided that I really loved mathematics. The Borsuk-Ulam theorem was one of those things that I just thought was too cool to not devote my life to. Anyway, little history here. This was conjectured by Ulam and proved by Borsuk. Apparently Ulam sort of sent very informally, maybe in a letter to somebody, said, hey, I think this thing might be true. And then Borsuk actually proved it. Here's the theorem. BUT means Borsuk-Ulam theorem. It says let f from Sn to Rn. Sn means the n-dimensional sphere to Rn be continuous. Then there is a point in Sn with f of x equal f of minus x. So minus x means the opposite point on the sphere. Every point on a sphere has an opposite point. So if you have a function from Sn to Rn, then and it's continuous, there must be you should think of this as there has to be like a pair of two opposite points who have the same value according to this function. And the Sn, usually I'm going to be talking about n equals 1 and n equals 2. N equals 1 would just be like the unit circle. N equals 2 would be a sphere, sitting in three-dimensional space. All right. I don't know if that sounds awesome to you. I want to try and think about it a little bit. So in the case n equals 1, it means any map from a circle to the real numbers has a point where the value of the function agrees with the opposite point. All right. If it's a continuous function. Okay. Like for example, consider this circle. I just have a circle with different color, I guess, different brightness as you go around the circle. All right. So the brightness, like I was just describing, you can encode the brightness as a real number as you go around the circle. Now, I'm not thinking this as a digital object. I'm thinking this as like an ordinary continuous circle with a continuous brightness that varies across it. You could encode that as a real number. In fact, you could encode the brightness as just like a real number between 0 and 1. 0 means black, 1 means white, something like that. Anyway, the brightness defines a function, S1 to R. And so the Borsuk-Ulam theorem applies. That means there must be a pair of opposite points with the same brightness. And this is, of course, not just for the picture that I drew, but for any continuous assignment of the brightness, there must be a pair of opposite points with the same brightness. This doesn't really seem obvious to me. But anyway, I just said, like, maybe those two. I don't know. I just sort of eyeballed it and circled them. But this must be the case for any kind of brightness that you draw around the circle. It's kind of remarkable, and I mean, there's no real obvious good reason why that should be true. It just is, that's sort of the hallmark to me of at least some kinds of mathematical beauty. Something that seems like that shouldn't be. Could that really be true? I don't know. Anyway, here's a brief tangent. Anyone care how I made that circle picture? I thought, when I was making this talk here, I got to have a picture of a circle with the brightness. I'm not really a computer graphics wizard, and I wasn't sure exactly how to make that circle picture, so I'll just show you how I did it. Start with a random image from the internet. I don't know if you've ever done this. I Googled most random image on the internet. You get lots of interesting things. Yeah, no, it was totally, I don't know if I have any kind of filtering on, but there was nothing, I guess nothing inappropriate. Depends what you mean by appropriate. But actually, the first 3 results involved people riding on things. That's like a theme. So what I'm about to show you is the 3rd result. The first result was a painting of Barack Obama riding a giant, like puffy dog. The second one was Hitler riding a sled in space with rainbows coming out of it. And then this is the next one. I just want to, I'll take a moment so you can take it all in. Yes. We got Chewbacca on a squirrel fighting Nazis. Anyway, so I started with this image, and then I turned it all gray, right? Then I blurred it because I wanted the colors to be continuous, right? Just this one, there's some sort of rough edges in the color. So I blurred it out, and then I drew a little circle on it, and then I just picked out the colors from that circle. There it is. All right. I hope that was interesting to you. Anyway, let's talk about the Borsuk-Ulam theorem a little bit more. So first of all, as you probably guessed, the proof is totally topological. So this is not a geometric fact about perfect circles. You can do this on anything which is circle-like in the topological sense. All right. This actually leads to some strange consequences in the real world. Like if you consider the equator of the Earth, which is like a circle, and the air temperature at any point, this Borsuk-Ulam theorem means that there must be a pair of opposite points on the equator of the Earth which have exactly the same temperature. I've tried to impress some non-mathematical people with this fact from time to time. And this is actually a very bad example because they'll be like, oh yeah, everywhere on the equator is the same temperature. Yeah, you're missing the point, right? That's not the point. This is a bad example if you're trying to impress your friends. They'll try to weasel out of it, all right? But, or like any heated metal ring. You can imagine like a metal ring and you just, at random, you heat up some of it in some crazy way. It doesn't matter how crazy a way you're heating it up. There must be two opposite points on the circle which have the same heat. It's very strange, in my opinion at least. This is actually true in all dimensions. Everything which I've been describing here has been just dimension 1. So in dimension 2, it's about functions from the sphere in 2 dimensions to R2. So the standard example that everybody talks about is if you have a function now like on the entire Earth, not just the equator, but the whole Earth, a function whose 2 real coordinates are the temperature and the barometric pressure. That gives you a function from the entire surface of the Earth to R2. And the Borsuk-Ulam theorem means there are 2 opposite points on the Earth which have the same temperature and the same pressure. Which, again, your friends might say, oh, yeah, well, that seems reasonable. No, it does not seem reasonable. Because you should not be thinking about the weather when you say something like this. This is about any continuous function. So, I like to say, instead of temperature and pressure, it's the temperature and like the, squirrel population density. Or anything you can imagine which varies continuously. And they're not going to say, oh, yeah, based on what I know about squirrels, there's, Anyway, it's a great fact, I think. Another version of this is if you have a balloon, which is S2, and then you just sort of squash it down on the ground. You can think of that as being a function from S2 to R2 because you are flattening it into the plane. And what this theorem says is that when you do that, no matter how you squash it down onto the ground, there must be 2 opposite points on the balloon which end up being squashed on the same point on the ground. Your friends should not think that that's obvious. If you just squash it straight down, then the North Pole and the South Pole will. But you can move it around in any kind of way you can imagine. There always has to be 2 opposite points. Anyway, it's a great theorem. I thought, let's just do, this will be real quick. This turns out to be easy to prove in dimension 1. Here's how you do it. So you take your function from S1 to R, that's the circle, to the real numbers. And we need to find some point x with f of x equal f of minus x. Here's the trick. Define this other function, g of x is f of x minus f of minus x. And now it's equivalent to find some x which makes g 0, right? We needed to make f of x equal f of minus x, but that's equivalent to this other thing, g being 0. Okay? Since g is real valued, I'm going to say without loss of generality, there should be some point where the g is greater than 0. Now, it may be actually that g is always negative. But then everything I'm about to say, you just sort of switch the signs on everything and it'll work out fine. So let's assume that there is some point where the g is positive. All right? And now you do some magic here. So if g of a is positive, it turns out g of minus a, what is that? First of all, plug into the definition of g. You get f of minus a minus f of minus minus a. Minus minus a is the same as f of a. So that's that next equality. And then I just sort of factored out a minus sign and switch it around. Eventually, you get minus g of a. So g of minus a is equal to minus g of a. G has this interesting kind of, it's like an odd function or something. That property, right? And so g of minus a equals minus g of a. And since I already said g of a is positive, that means g of minus a is negative. All right? This is almost over. I hope you haven't stopped paying attention. So that means this. G of minus a is negative and g of a is positive. Anyone know what I'm about to say next?
Has to get to there's a median value
Yeah, since g is continuous, I have a negative value and also a positive value. By the intermediate value theorem, there's some x where g of x is 0. And that's what we had to show. Right? So the end. It follows from the intermediate value theorem. Pretty nice. You can't really do this in higher dimensions because the codomain space in that case would be R2 or Rn, where the n is greater than 2. And then you can't use the intermediate value theorem anymore. So there's something like Sperner's lemma that you can use to prove that, yeah. Although it's called Tucker's lemma. And it's something, that's like the sort of combinatorial version of, they call it the combinatorial version of the Borsuk-Ulam theorem. Sperner's lemma usually you prove the fixed point theorem with, and the Tucker's lemma you prove the Borsuk-Ulam. Yeah. Usually it's proven with algebraic topology and the idea of the degree. A map on a sphere has a degree, and you can use the degree to prove these things. But anyway, I just want to do the dimension one. Let's go back to digital topology and try and sort of tie this together here. So I got to talk about functions in digital topology. If you want to do a digital, my goal for the next 15 minutes or so, 10 minutes maybe, a digital version of the Borsuk-Ulam theorem. All right. We got to talk about functions from one digital thing to another. So, and this is the definition that Rosenfeld gave for a continuous function. If I have two digital images, they're each two sets, and maybe they have their own different adjacency relations. It doesn't matter. You say f is continuous. It means whenever a and b are adjacent in x, then their values are adjacent in y when you do the function to them. All right. And it turns out this is a good definition. And in fact, this is equivalent to an epsilon delta definition if you consider the fact that the smallest possible epsilon in a digital space is 1, and the smallest possible delta in a digital space is 1. And if you just write out the epsilon delta definition using 1s for epsilon and delta, this is exactly what it gives you. So adjacent points in the domain map to adjacent points in the codomain. It's actually a lot easier to handle than the epsilon delta definition. So in the case of, since I want a Borsuk-Ulam theorem, we're going to care about the case where y is z to the n, that is playing the role of r to the n in our digital setting, and then x, the domain, is some kind of a digital sphere, whatever that means. All right. So let's start with dimension 1. I think the natural way to make sense of this in dimension 1 is in the codomain we have z over there with c1. That's in z to the 1. C1 is really the only natural adjacency that you can use. Where the domain is just a cycle of points. This is the digital version of a circle. So for instance, like C8 would be that. Now I'm drawing it here as a graph, although you can, if you want to think of this as a digital object, it would be, this thing, right? Eight points just arranged in a circle, okay? Not the middle one. All right. Anyway, C8 is like this one. But generally speaking, like a one-dimensional digital Borsuk-Ulam theorem should be about functions which start with a cycle of points and then give you integer values for each one. And those you could actually, so a continuous function in this case, say C8 to Z, is just an assignment of an integer at each of those points such that adjacent vertices have their two numbers differing by either the 0 or 1. Either they're the same or it changes by 1 when you go from one to the next one. So for example, this describes a continuous function on that digital C8 thing. All right. Anyone notice anything interesting about this function?
Has adjacent points that are the same. Or like opposite points that are the same.
Yeah, what about the Borsuk-Ulam theorem? Do you notice? You notice actually it does not have the Borsuk-Ulam theorem property, right? There are no opposite points here which have the same value for this function, even though the function is digitally continuous, right? You can just check. There's no Borsuk-Ulam point or no pair of opposite points which have the same value. So we got problems here. What went wrong? When I was first thinking about this, what went wrong? The immediate sort of, I lay the blame on the feet of the intermediate value theorem because that's what went right in the original proof. And that's kind of the weirdest thing that we used in that proof. Everything else was just a bunch of algebra, really. It turns out, actually, the problem is not the intermediate value theorem. In fact, there was a digital intermediate value theorem was proved by Rosenfeld in 1986. So it is true, actually, for any digital space, if you have a continuous map into the integers, if that thing is positive somewhere and negative somewhere else, it must be 0 somewhere in between. It's still true. So what exactly is the problem? Well, I thought it might be helpful. Let's try and just go through that proof. This is probably something you've done before. If you end up seeing something that doesn't work but you thought it should work, you should just like use your example inside the proof and see where it goes wrong. Start with that f that I said, and then let's build this function g of x, f of x minus f minus x. So for example, in our case, that thing on the left is that function I wrote before. The one on the right is f of minus x. I just flipped everything across the middle. All right. And now I'm going to draw that function g, which is you take the value on the left and you subtract the value on the right. And it looks like this. All right. Anyone see anything weird about this? What goes wrong in the rest of the argument? Yeah, the g is never 0, right? But actually, it's not because of the intermediate value theorem. In fact, this g here is not continuous anymore, right? Because from one point to the next, the values are jumping by more than 1. There's 2 points in which that happens. Okay. So the problem is this f of x minus f of minus x might not be continuous even when f of x is continuous. This in real analysis, this would be true, but it turns out in the digital theory it's just not true. All right. So this values of the g, they can jump by more than 1, and that's why the intermediate value theorem is actually true. It just doesn't apply to g because g is not continuous. All right. It turns out, though, and this is something that you will realize if you think about this for a moment, if f is continuous, then g can jump, but it can jump by at most 2. It's not going to jump by more than 2 because the values of f can jump by 1. And if you line them up just right, you can make it so that the g jumps by 2 because you're adding together 2 continuous functions. But it's not going to jump by more than that. So this g, it might not ever be 0, but if it's not 0, then it has to either be 1 or minus 1. Actually, it has to be both of them. If it's going to skip over 0, it has to hit the minus 1 and the plus 1. All right. So it turns out this is the correct theorem. If f is a continuous map on that cycle to the integers, then there's a point where the opposite points are equal or adjacent. Right? They might be equal or they might be adjacent. And this is the best you can do for a Borsuk-Ulam theorem for continuous functions. Actually, to my dismay, I discovered after I proved this myself, this was actually done by Boxer, who I know I should have known this because I already had this paper on my computer. I guess I just didn't read the whole thing. He did this in 2006. Actually, by the time I found this out, I had already done a little bit of a generalized version of this. And the generalization seems small, but actually I think it's kind of important. So we can improve on this a bit. What if your original function isn't continuous, all right? Maybe it's not continuous, but even so, there's got to be some biggest jump between adjacent points because the domain set is finite. And so I'm going to let L be the biggest jump that it ever makes between two adjacent points. All right. For a continuous function, this number is 1, but for any old other function, non-continuous function, it's something else. And I'm going to call this the Lipschitz constant. This is a term which I'm borrowing from real analysis. So in real analysis, this is the definition of the Lipschitz constant. If you've seen this before, then you know what this is. If not, I don't really want to get into it. But in the digital setting, again, I mentioned this already. In a digital image, there is a minimum distance between points, and it is 1. All right, so it makes sense, at least to me, it makes sense to we only really care about the situation when A and B are right next to each other. That's what really matters. And so if you let that denominator just be 1, then what you get is basically what I said above. The Lipschitz constant is the biggest difference, or the biggest distance between two adjacent points. All right. So a continuous function, a digitally continuous function, has Lipschitz constant 1, but non-continuous functions still have a Lipschitz constant. It's not going to be 1. This is very different from real analysis. In real analysis, if it has a Lipschitz constant, then it's automatically continuous. And there's some continuous functions with no Lipschitz constant. This is kind of the opposite. But anyway, actually, I found out also that Rosenfeld defined Lipschitz constant, so it was a decent name for me to be using, I guess. But he didn't really do much with this concept. Anyway, this is like a generalization of Boxer's theorem, I guess. This is our full-strength theorem in dimension 1. If your function has Lipschitz constant L, then there's some point where this point and its opposite point, their difference is less than 2L. So for continuous functions, the L is 1, and this would say the difference between the opposite points is less than 2, which means the distance is either 0 or 1, which is what I said before. They have to be the same or adjacent. Here it means, so even if your f is not continuous, and it turns out this is important for this application. Here's an application. This is a real-world application. I'm not used to doing this in my research, but here's a real-world application. This is an 8-bit grayscale picture. This is a Monet haystack painting, right? So this picture is, those are the pixel dimensions, 150 wide and 118 high. And you could describe the brightness of the pixels by a function like this. This is what I mentioned before. This is like 8-bit brightness on these pixels, all right? And this f here, the brightness, is not continuous. That's because there are some, if it were continuous, that would mean two adjacent pixels, their brightness can only differ by 1, which is not even detectable to the human eye. In fact, pretty much any digital image which you're liable to encounter in the real world will not be continuous in that sense, because you wouldn't be able to discern any features in the image if the colors were actually continuous, all right? In the real world, almost no images are continuous, but they do have this Lipschitz constant. Anyway, if we focus just on the boundary, the perimeter of this image, it's a cycle of 536 points. I did the math on that one. So this should be something which we can apply our Borsa-Coulomb theorem to. So the Borsa-Coulomb theorem should find opposite points on the boundary that have the same color. Not exactly the same color, because f is not continuous. But, this is what I said before, most real-world images are not continuous in that sense. But on the boundary, f has Lipschitz constant 23. I computed that with some fancy, not so fancy Python script. If you just look at the points along the boundary, the biggest difference in brightness that ever occurs between two of those points is 23. That means by our theorem, there must be opposite points whose brightness differs by less than 2 times 23. Remember, the conclusion of the theorem was 2L, right, which is 46. That means there must be two opposite points on the boundary whose brightness differs by less than 46. And in fact, these two are the ones who have the closest brightness, and their brightness differs by 13, all right? So it's kind of cool, real-world application, albeit something that I imagine nobody actually cares about in the real world, but it really is an application to a real-world image. I don't know, maybe this is useful for something. I'm not so concerned about that, though, all right? Let me just say for a few minutes, what happens in higher dimensions? This is like you could write this on your gravestone or something. Things get more complicated in higher dimensions. There are actually notable counterexamples to this in topology. A lot of times the low dimensions are harder, but in this case, the higher dimensions are harder. So people do care about digital three-dimensional digital images. These are things made of, these are called voxels sometimes. Something about that word I don't really like, but. So you could think of guys in Minecraft, or really any kind of discretized data. If you have just like a three-dimensional array of numbers, you can think of that as a digital image where those numbers, they might not, in your, wherever you got those numbers from, they might not actually represent the brightness of pixels or whatever, but you might as well. It's the same as an abstract object. It is the same. So any kind of discretized data, you could apply this sort of Borsa-Coulomb to. So the setting that we're going to do in higher dimensions, first of all, you have to say, what do you mean by a sphere in higher dimensions, a digital sphere? It's convenient to just make a loop of points that makes a circle. That, I think everybody, that's an ordinary thing to do. But to make a sphere is a little less obvious. Here's how I came up with the formulation for a sphere. So let B be an n box in Zn. That means just a product of n intervals. I call that an n box. And then the boundary of this is what we're going to take as representing a n sphere. And it's a natural thing to do. The boundary, actually, this would be a sphere of dimension n minus 1. So for continuous functions, I expect a theorem like this. This is what sort of we're aiming for as far as a higher dimensional Borsa-Coulomb theorem. The boundary of an n box would be an n minus 1 sphere. So if you have a continuous function from the boundary of the n box to z n minus 1, then you expect to have some point x with the antipodal points either the same, either equal or adjacent, all right? Turns out this is false. Here's a counterexample, which took me a long time to come up with this. I don't know, maybe it shouldn't have taken me so long, but I tried to prove this for a long time, and then I spend a day trying to prove it, and then spend a day trying to find a counterexample. Eventually, I came up with a counterexample. So consider this. This example is a boundary of a 3-box, and you should think of this is like 3 layers of a Rubik's Cube or something. So the left is the bottom layer, the middle is the middle layer, the right is the top layer. And here is the function. Each point is getting a value in Z2. And I will leave it to the reader to check that this is continuous if we use C1 adjacency. So remember, this is the adjacency which doesn't allow any diagonals. If you look from one point to another, for instance, between these 2 points, they are adjacent. And their values are also adjacent in Z2, right? According to the C1 adjacency, because they differ in only one coordinate. Great. It is, when you check this, you have to also remember sort of like the vertical adjacencies, like this one is adjacent to this one, up the next level. We can all do that, right? This function is continuous when we use the C1 adjacency, but it turns out, and this also you can check, f of x is not equal and not even adjacent to the antipodal point for any of these. For instance, if you look at the bottom layer, pretty much all of them have value 0, 0, and the top layer is all value 1, 1, and those are not adjacent using the C1 adjacency, right? Because they differ in both coordinates, except for that guy in the corner is 0, 1. But that opposite guy in that corner is 1, 0, so they differ in both coordinates, all right? If you want to check the opposite points in the middle, here you should be looking across because that's where the opposite points are in the middle. But again, they are not equal or even adjacent, all right? So that Borsuk-Ulam theorem doesn't hold even if the function is continuous in the higher dimensions. I guess maybe it matters which adjacency relation you use. If I use C1 both times, then you don't get a theorem. It turns out, and here's where I'm just going to sort of spit out, drop some science on you. Here's what I ended up coming up with. It does matter which adjacency relation you use. So here's some results, all right? The same setup if you have an n box and a map to Z n minus 1. Here are some theorems which are true, I think. So the paper is being refereed now, so I guess they might not be true, but I hope they are. So first of all, if f is Cn and C1 continuous, what I mean by that is it's continuous when you use the Cn adjacency in the domain and the C1 adjacency in the codomain, right? There's really 2 different adjacencies that you need to consider. Anyway, if you do this using sort of the top dimensional maximum all diagonals allowed in the domain, and no diagonals allowed in the codomain, then you do get a Borsuk-Ulam result in terms of adjacent or equal opposite points, all right? That was my first theorem. The next one is this one. The same is true if you use n minus 1 adjacency in the codomain. That is all diagonals allowed in the codomain, which is Zn minus 1, all right? Also, you get a true Borsuk-Ulam theorem. These are for continuous functions. I was able to do this for non-continuous functions with a Lipschitz constant, only in the case Cn to C1, though. So there are a lot of cases here which I didn't address in my paper because I couldn't figure out what was true and what wasn't true. So there's a lot of room for improvement in these results. I hopefully either I or somebody else will figure the rest of this stuff out. If you're interested, the paper. If this seems interesting to you, you can check it out. If you just search on Google digital Borsuk-Ulam. I've got the first result on that. It's the paper on arXiv. I don't use any real fancy machinery, so it should be readable to anyone who's interested. I guess that's all. Thanks.
Thanks, Chris. That was great. Questions?
Yeah,
Go back to the previous slide.
sure.
So the first theorem, you have Cn, C1. And the next one, you have Cn, Cn minus 1.
Right.
What about Cn minus 2 and the rest of the...
I don't know. Yeah, so I mean, my counterexample was a C1 and a C1, right? So there are certain versions of these cannot be true. In dimension, like in dimension 2, this was Z2, say, then the n would be a 3. So this would say 3 and 2. this would say 3 and 1. So it's true for 3 and 1. It's true for 3 and 2. But I don't know. It's not true for 1 and 1. Other than that, I don't have any idea what is and isn't true. I mean, the counterexamples, one thing that's hard is just like coming up with the counterexample. You have to, I'm not good at visualizing these sort of Rubik's Cube-like things with the 2 coordinates on each point. It's just, I don't have any good intuition about what is and isn't going to be true. Yeah.
Does it, so do these, the same results work? I mean, like these can be boxes. Like, do you have to take a Rubik's Cube, or could you take like?
Yeah, so the box B is just a product of intervals, and then you take the boundary of that. So it could be bigger, but I don't want to try and think of counterexamples that are bigger, right? That's even harder. So, yeah. And it doesn't have to have a hole in the middle of it, but I think if it doesn't have a hole in the middle of it, then you're going to automatically satisfy. Yeah, if there's no hole in the middle, then you have 2 opposite points which are already adjacent just in the original picture, and so by continuity they have to have this adjacent values. So it's only interesting when it's at least got some missing stuff in the middle.
Is there, oh, go ahead.
I don't know if this is what like you were trying to ask, but you're only dealing with boxes, not something that you would like normally think of like in like general topology as like topologically equivalent to an sphere. Like you're not dealing with like dodecahedron, like just like more complicated,
Right.
like things that would be normally topologically equivalent to a box, just boxes.
Yeah, that's right. Although, like the proofs of these are all sort of based on this graph theoretic model of what these things are. So it doesn't really matter that it's arranged as a rectangular box. Although, so if it as a graph is isomorphic to one of these other shapes, then it'll be satisfied automatically. Yeah, so it's more general than just boxes, a little bit. Did you have? No? Yeah.
Are there like, is there a Brouwer theorem in digital?
No. Well, yeah, so the Brouwer fixed point theorem says in this setting is that if you have I guess just one of these boxes, self-map, there must be a point, not a fixed point, but it's f of x is adjacent or equal to it. That is true. Yeah.
And does the C and the C1, C2, does that stand for clever?
No, I don't know what the C means actually.
Other questions?
Yeah. I really wanted, sorry, I meant to mention, I really wanted to have an example, like my so-called real-world example of the haystack. It would be nice to have an example like that, but in color, right? But in color, you need this to be 3 at least to get RGB color, and so the image itself has to be something in Z4, which is unsatisfying. So I think for color images, there really isn't a Borsuk-Ulam theorem. The dimensions just are not appropriate. Although that's also something maybe worth thinking about. Yeah. Thanks. Thanks to Winston, too. He saved me my technical difficulties with this stick. Yeah. He deserves it.